Hello guys, welcome! Today we are going to explore an earplug replacement for the rotary rocketry's PVC style engine. I designed the nozzle end plug to give a more stable platform to the washer and to stop the washer from turning at an angle before and during the cement pouring. It also replaces the paper disc used to prevent fuel leakage during the fuel pouring. The STL file link is included in the description should you want to print your own. I use PLA for the plug. Enjoy the video.
Okay, here's the 3D printed thing, plug, earplug replacement. You can see that it's hollow inside there. And what happens is it's the same dimensions that the earplug is here. From there up it is a little taller. But what it does is it holds the washer, the number 18 washer, it holds it in perfect horizontal position instead of letting it lean over to one side or the other. Now these things are made hollow because when it's inserted into the PVC thing and the cement's poured in, it don't want to come back out. So what I do is just take and break that off right there. This big piece will be gone. And then I take a drill and go down through the small tip that's hollow, and that'll open it all the way up into the core of the engine. And what little plastic is left there, what little PLA is left there is destroyed in the first few microseconds of the engine running, burning. So what we're going to do now is we're going to put this thing in here like that, and it's tight enough fit. And I got the finished product as a link below for the STL file. So you take the number 18 washer, put it right on top, just like that. You see the washer's in there, and it's horizontal, not angled some way, because the earplugs can get bent over and create a little bit of a angled thrust coming out of the engine, which over 1,000 feet can guide the rocket significantly off course. So, and then what we got for the top of the engine is a little bit of the cement up in the top for melt-through protection. So what I'm going to do now is glue the pipe to the engine, and I want to see how far this thing goes down in there. So this pipe, yeah, I don't do it in millimeters. It's a lot easier for me to think in millimeters than it is quarters and eighths and sixteenths and 74 thousandths of an inch. So the pipe is 116.8 millimeters. So now we'll glue that in there. A little primer, a little that. Need an acid brush, because that big old gobby brush that's in this can, it really just lays it on it. So this is 116.8. Millimeter. And number 18/64 nozzle and 3/4 inch core. And I'll guesstimate the fuel, how much is in it, but right now I'm not going to write anything on it. And one reason I want to see is how far this pipe goes down into this cap is, I'm trying to decide where I can pour the cement first, which will make it a whole lot easier, and then glue the pipe in, or if it has to be glued in first, which I suspect it does. I think I already went down that avenue once and didn't wind up with anything. And now we got the wonderful blue cement that gets everywhere, but you don't want it. Lay it on its side. We're going to go around this thing one time, back around it, and back around it. Give it a good solid coating. In fact, we could get a little more right here. Just like that. Put the lid on this squat. I'll spill it on me. I'll do this one. We're going to lay it over the side. We're going to put glue on the inside. Pretty generous coat. That works a lot better than using that big sloppy looking thing on the end of this cement. Now you get good glue, and we're going to twist it to get a good coverage. Everything will go on there like this. All the way down. Oh man, it went pretty far. Then got into my writing. So, I'll set that over here to dry for a minute. It don't take it long at room temperature to get workable. And what I've noticed is it puts a little, I don't know where you can see it or not, but it puts a little daub of cement down in there, a little purple ribbon that I don't want in the cement. Yeah. Anyway, that's what I got out with just that little bit of excess glue. Now I get to play whack-a-mole here. Whack-a-mole. Get that washer back on that plug. It ain't hard to do. Just when I turned it upside down, the washer being heavy just fell out. We do it this way. Oh yeah. Make sure she's fully seated down on there in the horizontal mode, and it is. Yeah, well, you can see or not, but it's in there. If I tilt it too far, that stupid washer will fall back off again. So now what we're going to do is that we're happy with that. Now, what happens if you make them solid and you can't get them out, then you got to drill them out. So this, it's the same diameter as the hole in the washer, so it's no big deal other than it's going to put out a little blob of melted PLA when it's burning. And I'm going to test fire this one and this one just to make sure that it ain't changing the characteristic of the engine. Well, there's some spare ones for next time. All right. Now we're going to put the cement here. Again, I left my wonderful little camera here in time lapse for where I was recording I bet that's too much, but it's enough, I know. recording a 3D printing process, and then forgot to take it out of time lapse. So when I looked at the video that I just made on these that I made, that was like nobody gonna be able to see that. I might break it up into photographs and make it work that way. And actually, I might not tell the truth, it actually did not record this at all. It recorded the assembly of the rocket naturally in stopgap time lapse. All right, we're going to have to estimate how much water we need here. It's always very easy to get too much, assuming you can find it. I got a pretty good little feel for what it takes now. And what I meant to do was put some in the bottom so it wouldn't stick, which I didn't do. And they almost hit it right on the tip there. It's just extremely close to what I want. Matter of fact, I think once I get all that incorporated, water incorporated into that, there's not going to be any need for any additional water and no additional cement. And I got gobs of extra. Get rid of that. So we're going to set this thing down, let it sit here for 60 seconds. Okay, we're back at the 20-second mark, so we've set for 1 minute. Per the instructions on the cement. Got a good homogeneous mixture here. Homogeneous. So letting that water soak in really stops any dry spots, which you don't want those. Alright, and now we'll pour this down the side and not try to pour it over the top of that thing, which of late has been a real challenge for me. Yeah, not too much. Just right to the tip of it. Just throw that away. Now I'm going to measure this. Let that plug fall out and all that stuff run out the bottom of it. See how much pipe is actually down in there. Okay, we got 85, 86 exposed. You're going to get up under one way or another, ain't you? So I said it was 116.8. 116.8 minus 85.77. 31 millimeters is what the cap took off the pipe. So now we'll see where 31 millimeters is on this. It goes all the way down in there, would be in business. 31. Come on, 31. All right, 31. So that's right to that, right to this lip, right there. It's going all the way down to that lip. 31 millimeters is the distance between here and the lip there is where it's stopping. So the cement would have to be poured no higher than that lip. And I bet you, when we look at this, it's higher than the lip. So it's going to have to be cement poured after it's glued together. Otherwise, it'd get a little short. All right. So we'll let that dry for about a day. Now I'm gonna have to go back and make this video over again. Well, crap loader. You know what I did do again? Like I didn't pour that out before I need it, while I still need it. I forgot to put my little dab in here in the top. And that's about a teaspoonful, maybe not even quite that much. I'm gonna work it around here a little bit. Okay, here we are designing the the plug. Yeah, just showing some of the parts that make up the STL file. The STL file is going to be included at the bottom on the Thingiverse. And I'll include the engine adapter as well. I think I forgot to do that on the other video. Anyway, so this thing is built by individual pieces, and I spend half my time trying to either find the item that I want to add, or how to move it, or how to do something else with it. And I never was able to get it hollowed out the way I wanted to on FreeCAD. So I went ahead and made the STL, transferred it over to Blender. And I've used Blender a lot longer than I've used FreeCAD, and I was able to get it hollowed out the way I wanted to. And part of that was at the very top where it's rounded, I wanted to have a rounded hollow section, so you don't get a big old thick ending in it when you try to punch through it with that metal punch. So as you can see from one of the parts of the video, when the first one was designed, it was solid, assuming that it could be pulled out. But the PLA, the way it's printed, has got a million little grooves in it, and every one of those little grooves and protrusions and divots get caught in the concrete, and it was impossible to remove, so I had to drill it out. And that was not acceptable, so I came back and redesigned it with the hollow inside, and that's worked real well. As on the, you'll see here in a few minutes the testing and the engine graph that it presented. The PLA that was left behind, it was a non-factor. So we just dribble through this and get these parts, getting them matched together, and get them joined into fusions that FreeCAD calls an item once it's two pieces are joined, two or more pieces are joined, I should say. So I'm not going to talk about it second by second. So I'll just let this run here, and then I'll come back and talk when we get to the next one. The problem I've had with Bandicam is that the audio and the video is not synced together properly. It will shift in the middle for some reason, and then it is just next to impossible to get it resynced. What we're doing here is we're putting it into the printing slicing software. And import it, and then we're going to slice it, then we'll print it. I use Personal Slicer with tree support, and that works real well for me. So we get it on there, and then we're going to print it out. Send it over to the printer, which is running a Pi web server. If it's a big project, I will put it on a SD card to gain the out of filament or power outage feature of the ELU. But when the Pi server is printing it, if the power goes out, you just lost it. You got to start over again. With a small item, I'm not going to worry about. So here we're looking at the Octoprint on the printer, just making sure it's sending it over there. And corner of the graph shows the temperatures coming up to operation temperature. Just looking at some of the things on there. The main one for me is to see it over in the left side in there. Okay, we're over here in Blender now. The item's been imported as an STL file, and you can see that the hollowing of it has been completed all the way to the little round tip up at top, so it's easy to punch through. And I left just enough PLA to make it stable but easily burn out. So the burning out of it when the engine ignites is not an issue at all, as you'll see on the test. And I don't know why I keep looking at it, but I do. I can use Blender a lot better than I can FreeCAD, but FreeCAD will do things Blender will not do correctly for me. So I have to use a combination of the two. Next thing we're going to do is... Okay, we got two here we're going to test. Built them yesterday. And they're 3/4 inch core, as you can see. 116 millimeter pipe with about 115, 18 64ths. The 4 is hidden. This is 1864 with 115 grams. It's 115 pipe, 115 millimeter pipe with the 2 end caps. And they both have the, this was the first attempt at what I did. And you see it left quite a bit of stuff in there, so I want to see how that works, because I still got 2 of those. And we're going to put a big old, what are we going to put on here? We'll call this A, okay? So it'll be an A. And this one will be B. And this one is the same as that, except it was the new version of thing that I made that you can punch a hole through it. What I use is a hole punch. These things are made really thin so that you can punch through them. Take a hole punch and just punch right straight through there, and it stays in place. You don't take it out like you do the earplug. And as you can see, it leaves a very small footprint. The big piece just breaks off, and then the little piece just stays in there. And we'll see how they do. I mean, it may be enough to cause problems. If the engine is close to exploding already, well, that might be enough to push it over the edge, especially this big old ugly one right here. We're going to try it first. So we blow the test stand up right off the bat. I may do it the other way around. Seems like it makes sense to test this one first. So we'll do B first and then A. All right. Next thing we do will be at the test stand. Okay, we have the engine all wired up to the test stand. Test stand automatically counts down for 60 seconds and then fires the engine. So even me, as slow as I walk, I have plenty of time to get around behind. I got a roll of hay on a tractor right here behind us. And so that was my safety spot to be away from it. And this is engine B with a cleaner, less PLA nozzle. And we're going to go for a test on it. Starting about right now. Good burn, a lot of smoke. Wind's blowing today, so it gets that cleaned out pretty quick, but I got away from it. I don't want to smell that stuff. So, the next one will be the A engine, which is the dirty one, because I was afraid it might blow up the test stand. But it didn't. It just behaved itself very well. So here we are with the second engine, which is the A, and what I called the dirty nozzle, or the more restrictive PLA nozzle that I will not be using. It was just way too much trouble to deal with drilling that stuff out. And here we go. 3, 2, 1, go. Now we got a good burn, and for some reason the wind kind of died down, and the smoke just hung there forever, so I could get back in there and take it back in the house. Not smoke just stinks. I don't think it's really toxic, but nobody wants to smell it that close. So now we're going to go into the engine power curves. Okay, we're going to look at the spreadsheet for the two engines now. We're going to start with the what I call the dirty one, or the B engine, and we're going to look at it first. So we open the spreadsheet that's already been created for it. And here you can see that it wound up being a G13. 57% G. Just clicking some of the results of the test. Next thing we'll look at will be the 5% grav. And you can see where it starts at a 5% cutoff and then goes all the way back down to 5%, which winds up being a vertical descent once the engine burns out. You got a good pattern here, good graph. You can see it better on the grams graph that it's vertical start with a peak at the top and no flat section. And then a fall off with a little burp at the end. A little over 2 seconds from the time the igniter's lit to the engine lights. That's insignificant as long as it don't have a peak, a small peak that would kick it off the rod and then have to wait for the large peak. So this one does not have that. When it starts, it goes. And a 2-second delay is not a factor at all. Unless you're racing rockets, then it would be. And here I'm just highlighting the fact that it's a peak and not a flat plateau at the top. The clean one, or the B rocket engine, will have a more of a plateau at the top. And you can see what time the test was run there. And it wound up being a G20. 67% G. And just highlighting some of the specifics of the test. Then we'll look at the 5% and then the raw data, which is in grams. The only difference is that the first graph is in newtons, and it's been manipulated with a 5% cutoff at the start and the end. And the grams is just the raw data out of the engine with no manipulation whatsoever. Most commercial engines that you buy is using I think it's a requirement that they use the 5% cutoff. In other words, it starts recording once the engine reaches 5% of the max thrust, and it stops recording, or the graph stops at when it drops below 5% of the max thrust. So you can see this one's got a little plateau at the top. If it was expanded out, it would be more of a plateau. It's also got a little bit of a slope to the max thrust. And when you look at it just straight in grams, it's not, you can see that little slope. It occurs right around about in there, and then it slopes over just a little bit. So it's not completely vertical, but it's very close enough. This one was a little slower lighting, it was around 3 seconds. The graph always starts when the igniter's lit. And it ends, you can see it goes all the way to the right, it ends for as long as the engine would burn. I could cut that down and make a more detailed graph, where you would cut the time slots down and have more of them in a shorter period of time. But then some of the engines that's lit with a fuse, that you can stop recording before the actual engine burns out. So it works good this way. It's much more accurate than using a bathroom scale and counting frames on a video. These times are absolute, and the thrust is absolute. Down to within, I'd say, 5 or 10 grams on the thrust. All right, guys, that kind of wipes out the end of this video. And I just stuck this one in because it was a co-project while I was working on the WTP2, and I want to go ahead and get it done with before I got confused on the videos between Bandicamp not staying synced with the video of the computer screen and cameras recording in time lapse when they shouldn't and not recording at all. It gets very confusing. So if we get too many things on the book at one time, I'll start getting confused what goes with what. So I'm a fairly organized person, but sometimes I'm not. All right, we'll see you guys next time. Be careful. Thank you. Okay, let me tell you, I've been to a county fair, a wagon wheel greasing, a goat rope, and a buzzard fry, and I've never seen anything like it. Take 2 seconds every time to press the like button. You hear what I'm saying? Thank you. Thank you very much. I'll be here all week.